We talked earlier about ionic compounds and about how they dissolve. And an ionic compound dissolving is also an equilibrium process. So we have the salt, it's convenient to talk about sodium chloride. We have sodium chloride dissolving into the water, but we also have some that's recrystallizing at the same time. And so it is an ionic process. So we have a term called the Solubility-Product Constant, and its symbol is KSP. And this is really the equilibrium constant for a specific kind of chemical reaction. So it's a chemical equation where we're dissolving a solid. And instead of calling it KEQ, the equilibrium constant, we call it KSP, the solubility-product constant. And as before, we omit solids from the equilibrium expression because their concentrations don't change. And a large KSP will mean that the compound is very soluble. A small KSP means that it's not very soluble. So let's look at that. So say for dissolving barium sulfate, and to write an equilibrium expression. Well, first of all, you have to write the equation for the dissolution. So what does this do when it dissolves? Well, it separates into its ions. So it separates into barium 2+ and sulfate 2-, SO4 2-. The equilibrium expression, but we're going to call it KSP, is going to be the concentrations of those two ions, and there were no coefficients, so we have no exponents, and it normally would be divided by the concentration of the reactant. But the reactant is a solid, and this concentration of a solid cannot change, and so we leave those things out. So this is the expression of KSP. And we're going to be limited in which ones we look at. We're just going to stay with the real simple ones in this class. So if you started with barium sulfate, solid, and you put it in water and it begins to dissolve, what do we know about the relative concentrations of barium and sulfate? They're going to have to be equal, right? Because if one formula unit of barium sulfate dissolves, you get one barium ion and one sulfate ion. They can't be out of balance because they came from the same thing. And so these solubility product constants are tabulated. Here is one that's in your textbook, and you'll probably have to look some things up in here to do the homework, which I realized last night, gosh, I need to pick the homework for this chapter. I'm sure you've been so unhappy that you haven't had any chapter 15 homework yet. But we just look these things up in a table. And so the KSP is a measure of the solubility of a compound. So let's go back here. So for this one, if KSP is a large number, that means that the concentration of barium and sulfate ion are high, which means that it's dissolving, right? If the concentration of these is very, very small at equilibrium, that means that it doesn't dissolve very much at all, and KSP will be really small. So let's look at this table. Look at this guy. Copper 2 sulfide, CuS. Its solubility product constant is 1.27 times 10 to the minus 36. That's really, really small. So that one is just basically insoluble. Almost none of it dissolves. And then you look at this one right above it, calcium sulfate. This is still a small number, 7.1 times 10 to the minus 5, but that's a lot bigger than 10 to the minus 36. So we can look at those KSP values and say, well, this one is more soluble than that one.
So that's the amount that it dissolves in water?
Mm-hmm.
During given a constant...
At a given temperature.
That's with a constant amount of water, right? Or is it any amount of water?
Well, it's any amount of water, because the concentrations are the number of moles per liter.
Oh, okay.
So if you double the volume of water, you double the number of moles as well. So it's not dependent on the volume of liquid. It is dependent on the temperature, though, because if you increase the temperature, generally you will increase the solubility. So write expressions for KSP for each ionic compound. So what we have to do is we have to write a chemical equation first. So AgI, silver iodide, that's a solid. That's a bad S. That's a solid, and that's going to dissolve and separate into its ions. So silver ion, we're going to have Ag, that's going to be aqueous. And when you do this, just showing the work for yourself, you don't have to put the state symbols in there, but I'm just going to include them to emphasize that we don't include the solids in the expression. What are the charges on those ions? Silver is +1, and we know that from the periodic table because aluminum's +3, zinc is +2, silver's +1. There was that stair-step pattern. And iodide is in group 7, it's 1 over from the end, it's going to have a -1. And so we look at that and we make sure that it's balanced, and it is. So what's the expression for KSP? Having iPad issues here. Come on.